Hi everyone, welcome back to the channel. This is lesson 9 of the Ansys Fluent Academy Beginner CFD series. In today's video, we are going to look at a very interesting CFD problem, the flow around the curved channel. We will go through the geometry, the boundary conditions, and understand the physics behind the setup before running the simulation. Here is the geometry we will be working with. It's a two-dimensional curved channel, kind of like a quarter band. The inner wall has a radius of 4 meters and the outer wall has a radius of 6 meters, giving a channel height of 2 meters, as you can see here. The fluid flowing through this channel is water, and it enters with a constant velocity of 10 meters per second at the inlet. The flow flows this curved streamline around the band, just like you see in the figure. At the bottom point, labeled bottom here, the pressure is 40 kilopascal. We will then calculate and compare the pressure at the middle point, which is 1 meter above, and the top point, which is 2 meters above this bottom point. Gravity, actually here as you can see, acts downward in this problem with an acceleration of 9.81 meters per second squared. And since the flow is assumed inviscid, we are neglecting viscosity effects, meaning we will consider a uniform velocity profile across the channel, as you can see. So the main goal here is to find out how the pressure changes as the fluid moves upward along the curve section. First, using an analytical solution, as you can see here, we can see some results and then comparing it with the results we get from the Ansys Fluent. So for example, as you can see here, based on this equation for the inviscid flow, for the middle point, as you can see, 1 meter up from the bottom, the pressure is 12 kilopascal, and for the top one, it is minus 20 kilopascal. So we will check this solution and compare with our CFD results. And for the creating and generate the mesh, we will use quad mesh, and for all of these edges, we will use 13 as the number of intervals, as you can see here. All right, that's the setup for our problem. So in the next step, we will start like other previous session with Ansys Workbench, build the geometry, and prepare the case for simulation in Fluent. So let's get started. So I will open the Ansys Workbench and again use the Fluid Flow Fluent and drag and drop to this project schematic. So I will save the project and name it as a flow around the curved channel and save the Ansys Workbench project, and then I can double click here and change the name of this project here. Then I will select the geometry and then change the analyze type to 2D, and then double click on the geometry here to open the SpaceClaim as our default geometry modeler. Okay, now let's start into the SpaceClaim here. So this is our geometry. We can start with the sketch that we are now there. First of all, I will select the plane here, XY plane, and then use the plan view to have a normal view on it. So I can start with creating two circles. The first one is the circle with the diameter of 6 meters, the outer one, and for the inner one, I have a circle with the 4 meters. So I can start with the circle here, click on the circle, but I need to have the center at, above the origin point. So I will first select the Cartesian dimension. So now I can select the center of circle and define the center point of the circle. So I click here, and then as I know, it is 6 meters, but maybe it is better first go to the file, because I'm working with the meter as a unit. So I will go to the SpaceClaim option here, and then in the unit I will change the length unit to meter and then press on OK. So now again I will select the circle and then use the Cartesian dimension. Now I am going to define the center point of the circle. So first I will select the origin point, then I will use the tab key and write the 6 for the point, and then press tab key on the keyboard and write 0. So now I have this center here, 6 meters above the origin, and then I can select the origin point, or just write 12 as our diameter. So I will press 12 and then enter. I will use escape to exit the sketch. You can check the dimension and the measure. You can see the circle diameter is 12 meters. It means that the radius is 6. So I will do the same for the inner circle. Use the circle, select the Cartesian dimension, use this point, origin point, and then from here I will again go to use the tab key, write 6, use the tab key again and press and write 0. So from this origin I will go up 6 meters up, and then for the diameter I will select 8 because the radius is 4, so the diameter is 8, and I will write 8 and press enter. So now I have, and then press escape to exit the circle. Now I have two circles with radius 4 and 6 for these two. Then I can select actually two lines. Actually this is a 90-degree bend curve pipe actually. So I can start with the line and select, use the angle of 225 for example. So first I will select the line here, select this center. So I need actually something here. I will write 6 for this distance and press tab key. So I will go to the angle. So I can type 225 degree. So I have this line now, and I can do the same. Select this center of circle and type 6 on the keyboard. Press tab key on the keyboard and go to the angle. And this time I will write 315 degree. So it will be, and press enter. So it's a 90-degree angle of actually here. So you can check this angle also. I will go again to the measure, use the measure tool, select this line, hold the control key, select the other line, and as you can see it's a perpendicular, and so it's 90 degree. So that's okay. I will go to the sketch, press escape to exit the measure tool. Then I need to use trim in the modify of the sketch. So trim away is the tool that I can use and delete the extra lines like this one, this one, this one, and this one, only just by clicking on this line. So now I have this curve here, and then press escape, and I can select this end sketch editing to exit from this sketching plane, and then as you can see I have a surface here. Now it is time to go to group and select our name selection. So you can see this is inlet, this is outlet, and these two are wall. So I will use the select tool and then select this one. Press on create name selection or use Ctrl G, and then write inlet for this one. Select this edge and use Ctrl G, write outlet, and then I can select this line, hold the Ctrl key and select the other edges here at the bottom, outer edge. Use Ctrl G on the keyboard and write wall and press enter. So now I have defined the name for different edges, and it will be our actually boundary condition later on the Ansys Meshing and also in the Fluent. So now I can bring this down and close the SpaceClaim, and then press on the save button to save, and then start the Ansys Meshing by double clicking here on the Ansys Meshing. So it is starting to open the Ansys Meshing. Okay, now the geometry has been imported into the Ansys Meshing, and we have our geometry here and also the name selection we defined before in the SpaceClaim. Now we can just work on the mesh. As you can see here, we are using quad mesh, and number of intervals will be 30 for all of these edges. So we can start. First click on the mesh, right click on it, then use insert and face meshing. So you need to select this surface, I will do it, and then click here and press and apply. Just check this one should be quad type, so that's okay. After that I will again select on the mesh, right click, insert, and then sizing. I will select sizing. Then I will go here and select edge selection here, and then I can click on this edge, hold the control key and select all other edges, these 4 edges actually, and then press on apply. So 4 edges has been selected for this one. In this tutorial we just use some rough mesh, but after that you can practice again and change this mesh sizing later on. So here I will just go to the type of the mesh, this mesh sizing, and change it to number of division, and change this one to 30. So as you can see here, I have this type of mesh for all edges, this division, and then press right click on the mesh and then generate the mesh. So as you can see, we have a very rough mesh here for this tutorial today. Just the latest step here is to update the mesh and send it to the workbench, and as you can see, the mesh successfully transferred to the workbench. So now I can close this Ansys Meshing also. Okay, as you can see, this part also has been checked. I can save the project, and after that I can run the Fluent launcher, Ansys Fluent launcher. So double click here, use the double precision, and then change the solver processors to 4, and then press on the start. Okay, so now the mesh imported here into the Ansys Fluent. We can start with the check the size of the mesh. There are 1110 cells for this one in this geometry. I can also use the mesh check, and as you can see, the minimum volume is a positive value, so that's okay, there's no error here. And this is our inlet, outlet, and these two are wall. So I will keep geometry here, and now we can start with the setup. Okay, and one more thing, we can go to the scale and check our the minimum and maximum in the X and Y direction. As you can see here, the minimum value for Y is not 0, and this is because of the mesh generation here and the geometry we have created. It's a little bit more than 0, and as you can see, the minimum, X and maximum are between -4 and 4 meter here and here, and the maximum value for the Y is roughly 3 meters here in this point. So now I can close this one. As we discussed, this is an Inviscid problem, so we can keep these settings here for now, and then go to our model, double click on the viscous, and then change this turbulent model to Inviscid. So I will press on Inviscid and press OK. Here the working fluid is the water liquid. So here, as you can see, default value is the material for the fluid is air. So I will select a new one in the material, go to the Fluent database. This is the same process as previous videos, and then select the water liquid, select here, press and copy this one to Fluent database here. We don't need to use energy equation, so I will keep it as off for now. Then I will close this material, and as you can see, the water liquid has been added under the material. So I can use this material now in the cell zone condition. I have one cell zone, which is a fluid. So this surface, I can double click on it. The default material is air, so I need to change this one to water liquid. I will select this one, press and apply, and then close this window. As we discussed, the operation condition, the pressure is 40 kilopascal, so we need to go to the physics and use the operation condition. So here I will change this operating pressure to 40,000 pascal, 40 kilopascal. Then select the gravity in this y direction. So here the gravity in the y direction is minus 9.81. So I will enter here, and then press on the OK here to close this window. Now I will go and check the boundary condition. I have one inlet for here, and this is velocity inlet. I will double click to open it and use the velocity magnitude 10 meter per second. It is normal to boundary. It means that it is in this direction, normal to this inlet boundary. So I will apply and then close this window, and then for the outlet, you see it's a outlet. I will change this boundary condition from pressure outlet to outflow. So I will right click here and then change the type to outflow here. So I will select this one. You don't need to change anything here, any input here. So I will close this one, and as you can see, this is the wall, these two, and we don't need, as we are not using the energy equation, and we don't need to do anything also here. Then I will go to the method for the pressure velocity coupling. I will change this one to simple C here, and then for the pressure I will use the PRESTO and second order for the momentum. So I will keep this value, change this value and update. Then I will go to the outline view again, and then press on the control. This time I will change this under relaxation factor. For the pressure, I will use the 0.9, and for the density and the body force, I will keep this 1 here, and the momentum 0.7. So here I can just change this one. I can actually go to the monitor and then residual here. You can keep this one or decrease the value here, but I'm just keep this value. But this time for this tutorial, I will uncheck this check convergence. It means that if you reach to this value with your iteration number of iteration, the Fluent will not stop the solution, and it will go until the end of the number of iteration. For example, in this case we have, for example, 100 iterations, so it will go on until the end of this iteration. It will complete it all the 100 iterations, and if it reaches this value, it will not stop. So I will just uncheck this value, and if the convergence has been set, it will not stop. So I will press an OK here. Okay, so before we start solving, we need to create a custom field function. For this one, we should go to the user define and use this field function, custom field function calculator. By default, Fluent calculates the gauge pressure, which is the pressure relative to the operating pressure. It doesn't automatically include the effect of gravity, but in this problem, gravity acts downward, as you can see here, and the pressure changes with the height. To capture that hydrostatic effect, we will define a new variable called pressure, using the formula of absolute pressure minus density multiplied by G, 9.81, multiplied by Y, I mean in this direction. This equation simply adjusts the absolute pressure by subtracting the hydrostatic component rho g y, so that we can get the true total pressure distribution in the vertical direction here. We will later use this custom pressure variable to monitor and compare the pressure value at these 3 points, top, bottom, middle, and bottom, with the analytical results that we derived earlier here. So that way we will be able to see how closely Fluent simulation actually matches this theoretical solution. So let's start. We can just call this one as, for example, pressure, and here we need to define our equation. So I'm going to define this pressure formula. So it's the absolute pressure, and this is the name of this new function, pressure here. So here we can define our formula. Just press click here, and then from this field function under the pressure, I can select the absolute pressure, and then if you go here, it is minus density. So I press select, so absolute pressure is here, it's minus, so I will select this sign here. Then I can go to the density, select density, multiply by 9.81, and then multiply by y. Here you need to go to the mesh and select your y coordinate and press select, so you will see you have this y also here. I will call it as pressure again, and then we can define actually this formula. The pressure is equal to absolute pressure minus density multiplied by 9.81 multiplied by y, which is same as this equation. So now I can close this field function window. Now I can define 3 points here. These 3 points, bottom, middle, and top. For the creating the actually the points, I will go to the results, and under the surface go to the create and then select the point. So you can just use the with the right clicking on the mouse, you can get the coordination here. I will select 0 for all of these 3 points. So x coordination is 0 meter, and for the y I can select, for example, this value. This value is maybe I can reduce this one also. If it's not in your domain, so you cannot create actually this point. So I will just put one small value here, one coordination, and then call this one as bottom, and then create this point. Then I need to create the second point, midpoint here. So it's the coordination is 0 and 1. So I will call it as mid 0, and here it's 1 meter. Then create this one, and for the top one, I will just change the y coordination to 2. And as you can see, the previews here. So I will create this third point here. And if I go here, you can see I have this bottom, middle, top. I will select and display again. So I have these 3 points on our domain here. So now I can close here. So for these 3 points, I can to have the values in the solution, I can go to the report definition, double click here. Now I can define 3 actually reports for so I will go to the new here, and under the surface report I will select sum. So for example I can call as pressure bottom, and so on the field variable I can go to the custom field function. The only option is this pressure that we have defined before, and then it's for bottom, so I select the bottom value. I will tick this print to console, and I have report file and report plot. It will be added later on here. So I will press on OK. So I have the first one here, and if I open this one, you see the pressure bottom is here, and I have also one report file for this pressure and one plot here. I can do the same for those 2 other points. I will select sum also here, and then call it as pressure mid. Then here again custom field function, this time it's middle, and then print to console, OK, and then again go to the surface report, use sum, and then pressure top, use custom field function, and then top, and then print to console, OK. Close this window. As you can see, I have a 3 report file and 3 actually plots. So you can see during the iteration these 3 plots, and also the data will be saved in these 3 files, and also you will see on the console these values for these 3 points. Without delay, we will go to initialization, double click on it. I will use the standard in this simulation and use the inlet. These 2 values will be updated automatically. Use initialize. So it has been done, and then I will go to the run calculation, double click here, and then number of iteration I will select 100, and then press on the calculate. So as you can see, the solution has been started to run. This is the pressure for the top. You can see the value is now a constant value, and you can check for the middle and the bottom plot, and this is our residual. It is converging, and because we didn't check the convergence check, so I will press on OK. So it went under the 1e-9. We checked, we use the default value for residual 1e-3, but as we unchecked the convergence point, so it went until the 100, and then as you can see, we solve the solution with all 100 iteration that we select here. And if I extend this one, you can see the pressure top, mid, and bottom actually print out into the this console here. So if we check this value here actually, so for the bottom it's almost 40, as you can see here, this value for the bottom, it's almost 40 kilopascal for the bottom. For the middle point, the pressure is almost 30 kilopascal, but the analytical value is 12 kilopascal. So there is some errors between these 2 values, analytical value here and this numerical value. And for the top point, it is minus 18 minus 18 kilopascal, which is the here is minus 20 kilopascal. So there is a error here also. And now I can go to the outline view here and go to the graphics for creating contours. So before that, I can go to the workbench and save the project here. So the results will be saved here, and as you can see, solution and setup and solution has been ticked for now until this session. I will double click on the contour, and then I can write contour pressure, and I can select the pressure here and then display. And as you can see, this is the pressure contour, a static pressure actually here. You can also use this custom field function that you have created and display. So you will see the value here. This is roughly 40 kilopascal, as you can see here, and this point is roughly, as you can see. Let me just display through the mesh, display here, deactivate this one. So I will have this value here and then save and display. So as you can see, the value pressure value actually here is roughly 40 kilopascal. For this middle point, it is roughly, as you can see, 12 kilopascal, as you can see here. And for this top value, it's roughly minus 20 kilopascal, which is corresponding to these values: 40 kilopascal, minus 20 kilopascal, and 12 kilopascal for these 3 points. And the final part is to creating one line here into this channel from here to here, and generate XY plot on this line. So to create a line, I will go here under the results surface, and I will select the line and Rake. I will call it as center line, and for the first point I will select 0 and 0, and for this x1 and y1 I will select 0, and also here 2 meter. You can also use this tools here, select points with the mouse, but I will just enter manually here and then create this one. You can go here and find this center line and select this one, display. As you can see, this is here in the middle. I can deselect these points and display inlet. So I have this inlet outlet here, and also this point, deselect this button and display. And then I can close this one and then go to the plot to create a XY plot here, or you can use XY plot here. So I will go here and then select a new XY plot. So first I will call it as XY plot for pressure. Then as the actually in the graph that we will see, the position will be shown on the X direction, but the value is on the Y direction. So here I just change this plot direction to 0.0 and 1 for X and Y respectively, and then I will go to custom field function, and here I will select the center line and then save and plot. And as you can see here, we have this pressure on the XY plot, and as I told you before, in the X axis we have the position of the center line, I mean in the vertical line. So this is corresponding to coordination of 0 for the Y direction, and this is 2. I mean, I can show you here. So this point is corresponding to the Y0, which is here, and here actually this is the Y, because we are working on this center line. So this point is corresponding to this top value, and as you can see, the pressure in here is roughly 2E4 or 20 kilopascal actually here, and the value for here on the top, on the bottom actually, bottom point, which Y is 0 here, so it's 40 kilopascal as you can see. So okay, and that completes our simulation of flow around the curved channel. We started from geometry and meshing, set up the boundary conditions, and run the case in Fluent. Finally, we compare this CFD results with the analytical solution, and as we saw, the pressure value matched quite well with only small differences. I hope this lesson helped you understand how approach curved flow problems and how to use Fluent effectively for this type of analysis. Thanks for watching, and I will see you in the next lesson.